Okay, to calculate efficiency, we need to calculate the average power out over the average power in. And so the average power in is going to be the product of the voltage and current of the two power supplies, because they're both giving up power. We're going to add those up and then integrate over a period and divide by the period. But since the voltage here is the same, and a constant, it's just a 5 volts, I'm going to pull that out in front. We have an integral then of the current, which we just solved for, which is going to be the peak value divided by pi. You'll have to go after what is that peak value. So we've got the emitter current of 13 and 14. We've got to find a peak value. Like I said, the emitter current and collector current are about the same if you're in the active region. And that's going to be the output voltage peak divided by R sub L. But we know the output voltage peak is the input voltage peak minus the base emitter drop, in this case at Q11. And for transistor 14, the collector current is going to be equal to the output peak, really negative, divided by R sub L. And we found that the output peak was minus the input peak plus the emitter base of, in this case, transistor 12. So the minus signs cancel and we get basically a similar expression for the base emitter and the emitter base drop. So basically you get twice the power supply. This is really the difference of the plus 5 and the minus 5. And then subtracting off really the drops across the p-n junctions. So we can put this in now for these values, here and here. Pull out the R sub L, and we can add the fact that we've got twice the input peak, which is really the peak to peak of the input, minus the two drops across the emitter base and base emitter of the NPN and PNP. Same definition for the power out. It's the integral of really the voltage times the current, which in our case we labeled as V out and I sub L. Now, if there's no distortion and you have a perfect sine wave, it would also be the product of the RMS voltage times the RMS current, or you could take V squared over R sub L. These are definitions from ECE 202. Well, let's neglect the distortion, just to get a rough approximation on the results. If you have a sine wave, the RMS value is the peak-to-peak value divided by 2, and then dividing by the square root of 2. We're going to square that and divide by R sub L. Okay, the 2 squared is 4, and then the squaring of the square root of 2 is just 2, so you want to be getting 8 in R sub L. The peak-to-peak value we've just solved for, it's going to be the, well, we'll do it again, I guess, the positive peak minus the negative peak. And so it's the peak of the input minus the base emitter, and then it's the emitter base minus the peak of the input. So again, the minus signs cancel here, and we're going to get twice the peak of the input, and then the subtracting of the two diode drops. And now we're dividing by 8 R sub L. So the overall efficiency then is the ratio of the average power out to the average power in. You multiply that times 100%. In electronics, they use the letter eta for efficiency. Of course, that may be confused with the eta of the transistor. Those are two separate things. Okay, so I'll take the two results together now. So V out, the power out is this expression here. So you write this over here. And the power in is the expression up here. We can just take the reciprocal of that, which has got this expression times VCC, and then the reciprocal of pi over R sub L. Now what's kind of interesting is that this is independent of R sub L. Although I labeled the speaker in this case as a resistor, it's really an impedance that's changing with frequency, but it actually drops out, so it's independent of that for calculations of efficiency. And of course this term right here is the same as this term, so we lose one of those. And so we've got this quantity divided by VCC, and then pi over 8 times 100%. So in our SPICE simulation, using the values that we had for the turn-on voltages, these would be at the peak value. There is a value just as it's starting to turn on, and remember that the drop across the base emitter junction, or that of a diode, is going to slightly increase with current, but we're actually calculating this at the peak value of current. So it's just taking the 5 volts minus the peaks to get the values of those. You want to get about 66.5%. Theoretically, if these two base emitter and emitter base drops were negligible, then this term would drop out, and we would just have twice the power supply divided by the power supply times pi over 8, and so what you're going to wind up getting is pi over 4 times 100%. So the best you could do is 78.5%. This again is at full signal out. We don't normally listen to things like that, although some people do, but usually we're really a small fraction of the maximum power out. The real advantage of this structure is that when the input is 0, the output is 0. So you really can't calculate efficiency because it's 0 divided by 0, but definitely the power coming in is 0 because we're not drawing any current from the two power supplies if we're not putting out any voltage. Let's do another point here. If you did half the power supply, In other words, if you made the sine wave coming in only 2.5 volts, then you'd have this multiplied by 2, but we still have a 5-volt supply. So the efficiency actually drops to 27.3%. This is one of the characteristics of this type of an amplifier, that the efficiency varies, but the good news is that the best efficiency is when we have a maximum input, and that's of course when you're dealing with the most power. But you have to remember that we're normally playing music at much lower than the maximum values. We aren't running that efficient, and so we'll look at other schemes of efficiency and other courses to try to boost this for low signal levels. Let me back off the maximum output and let's lower the input, say, to 4 volts. You can see here again, my output voltage actually divided by the 8 ohms that I have there is this as a current waveform. A little bit more distortion because I've lowered the input. This is the current that's actually coming in, or really coming out of, I should say, the input voltage source, V sub S. So we could calculate the current gain, not really on the average, by taking the difference of these two over the difference of these two. And you can see here it's about 14,000. So we have a very high current gain, which is what we're going to need for our power amplifier, but a voltage gain of around 1 or so. So here we've got the load current I sub L. It's going to be equal to the collector current of 13 plus the emitter current of 11. That's this expression here. But the collector current of transistor 13 is related to the base current by a factor of beta. And then the emitter current of transistor 11 is going to be equal to the base current, which is right here, of 11, and then plus the collector current, which is the base current times the DC beta. Now the base current of transistor 13 is the collector current of transistor 11, which you could then also say is related to the beta, DC beta, times the base current of transistor 11. So now we've got a common I sub B of transistor 11, and what we've got here is beta squared plus beta plus 1. Now if beta is over 100 or so, then squaring it is much, much larger than these two terms. So roughly it's beta squared. So the advantage of this structure is that we're able to kind of amplify the current by this adding of this third and fourth transistor. If we had a current gain of around 14,000, then we're looking at DC betas around 120. The voltage gain of the power amplifier, as we saw, was approximately 1. So if we're going to try to boost our signal from the AM or FM part of the radio, we'll need to have a preamp with the power amplifier so we can get some voltage gain besides just current gain. Just look at a simple one transistor scheme. Suppose that we could adjust this biasing on the base side to give us a collector current of about 1 milliamp. That's sort of where the betas of the transistors are about their best values. Suppose that beta is 150, which is roughly the nominal value of the transistor we're using. At 1 milliamp, we're looking at a base current of 6.67 microamps. So we could use that then to calculate the AC parameters of GM and RPi. So given I sub C of 1 milliamp, and then roughly eta F being typically around 1, and then V sub T around 26 millivolts, we're looking at about 38.46 millimos for GM. And then for RPi, it's eta F V sub T over I sub B. That'd be about 3.9 K. The value of CPi and CMu are pretty small. Suppose that CPi is around 20 picofarads and CMu is around 2 picofarads. Then, if we're looking at frequencies in the audio band from about 20 Hz to 20 kilohertz, the impedance of the capacitor will be decreasing as the frequency goes up. But let's take a look at the highest frequency. That would give us a reactance of the capacitor in magnitude of 1 over 2 pi 20K times 20 picofarads, and that would be around 400K. Remember, that's in parallel with RPi. Since RPi is around 3.9K, then this is pretty much negligible, even though it's an imaginary term. Likewise for CMu, with being smaller, be almost 4 megohms. Of course, that's in parallel with RMu, which is very large resistance. So both of these look like pretty high impedances, and then as we did in 302, we really neglected all these things because they really were very large compared to the things in series or in parallel with them. Now an early voltage for our transistor would be somewhere in the range of 100 volts or so. And so just using the approximation formula earlier in this lab lecture, 100 volts divided by the biasing of 1 milliamp would give us about 100K. Suppose that R sub x is around 10 ohms, then that's in series with about 4K, so basically it's about R pi. So we're pretty much back to the model we had used in 302 with an R pi, a GM V pi. You could also use beta naught IB, the AC beta times I sub B, and then now a parallel resistance with our current source to take into account the slope of the VI characteristics. So we take our transistor circuit and we put in an AC model for every component. The battery, it looks like a short circuit for AC because there is no change in voltage or a change in current, and the same is true of the power supply here. And then we have another battery down here. And then the base emitter was here, and then the collector emitter was here. So we're going to put in our GM V pi here with R0 in parallel, and then an R pi over here with V pi across it. Okay, with all the short circuits, now let's just redraw this. This is all shorted, so we're just along here, and then R sub C folds over and it's in parallel with R0. So just symbolically then, the gain from here to here, and we'll label this as V sub S, this is going to be feeding our power amplifier. So we're going to have all this current flowing into this parallel combination. So GM V pi times R0 in parallel with R sub C. And V pi actually is Vn. So just replace the V pi by Vn. Now if this resistor here is about 3.3K, then what we've got is 100K in parallel with 3.3K. And you pretty much could throw away the 100K. It's much, much bigger than the 3.3K. And that's exactly what we did in 302. We just ignored R0 for most of the course because it really is negligible with most things in parallel with it. So given the GM calculated for a biasing of 1 milliamp in the 3.3K resistor, we're looking at about a voltage gain of minus 127. So we'll get a phase inversion. That's going to multiply the gain of 1 in the power amplifier. Overall gain would be around 127. So we get large voltage gain, and then of course a very, very large current gain, really added on to the current gain of this stage too.